The range and interquartile range are two other measures of variation. Ashley used a stopwatch to determine how quickly she could enter the combination to open her locker and recorded the data below. Let's first put this data in order. Then we can find the range by taking the largest number minus the smallest number. So 95 minus 40 is 55. Before we can find the interquartile range, we need to find a key set of 5 numbers: the minimum, quartile 1, the median, quartile 3, and the maximum. We already know that the minimum and maximum are 40 and 95 respectively. We know how to find the median by crossing off numbers to find the middle. I see that 45 and 50 are in the middle, so I add them together and divide by 2, giving me 47.5. To find the first quartile, we look at the first half of the numbers and find the median of that first half. The median is 45. Similarly, with the second half of the data, we find the median of the second half, so 50. It should be known that 25% of the data lay between 40 and 45. 25% of the data is between 45 and 47.5. 25% of the data lies between 47.5 and 50, and the last 25% of the data lies between 50 and 95. Interquartile range is the difference between the middle 50% of the data. So we're particularly interested in 45 and 50. So to do this, we subtract them and we get 5. Doug recorded the grams of sugar in each of his favorite sodas. Describe the variation of his data set using range and interquartile range. So we know we need the minimum, the first quartile, the median, quartile 3, and the maximum. Putting our data set in order, I see that the minimum is 62 and the maximum is 120. Subtracting the 2 gives me a range of 58. The median is the middle numbers, so I look at 66 and 70 and need to divide by 2 to find their average for the median to be 68. The first quartile is looking at the first half of the data and finding the median of the first half, which we can see is 65. The quartile 3 is the second half of the data, finding the median of that, which is 78. Finding the interquartile range, taking 78 minus 65 to get 13. Ricky thinks that since the mean amount of money spent on snacks is greater than the mean amount of money spent on lunch, the mean absolute deviation of the amount of money spent on snacks will be greater. Is she correct? Explain why or why not. So I took a moment to kind of write down all of the sentences into an inequality. Ricky thinks that the mean money of snacks is greater than the mean lunch of snacks. She also thinks that the mean absolute deviations of the money of snacks is greater than the mean absolute deviation of the money of lunch. So looking at our data that I've calculated for us, I see that the mean lunch is $3.90 and the mean snack is $5.05. I also see that the mean absolute deviation is 22 cents and the mean absolute deviation of snacks is $1.64. In both cases, the snacks are greater than the lunch. However, we have to know what each part means. The mean is the balance point of the data. So this means that she must have spent more money on snacks because the mean is larger. However, the mean absolute deviation simply states the average distance of the data from the mean. So in this case, the larger the number, the more spread out the data is. So just because the snacks have the larger number doesn't necessarily mean that she spent more, and that should be reasoning. It just means that the snacks are more spread out. So we can see that if we were to use a dot plot, the top represents the money for lunch. Notice that it's all clustered together, whereas our snack data is more spread out. Aria and James recorded the number of television shows they watched each week for 5 weeks. There's their data. Which statement best compares the variability of the two data sets? It looks like we're talking in range. It looks like we're talking about the mean deviation, as well as the median. So I've listed for us the mean and the mean average deviation for both of them. We cannot look at letter A because the range does not tell us the variability of our data, how much our data varies. Similarly, the mean somewhat shows us, however, the mean average deviation is what we're really looking for because this tells us how spread out our data is. So Aria's is very much more spread out than James. James's data is more close together to the average. Let's analyze the center, spread, and shape of the data. We'll start with the center of the data collected on the right is meter jumps and the long jump distances. So the measures of center I'm giving you, the mean is 2.89, the median is 3.17, and there is no mode. But we need to know, well, which one is best when we want to look at data itself. So depending upon the type of data we have and the distribution of the data tells us what might be the better one to look at. This is continuous data because it's continually being measured. Discrete data is data that you can collect, such as how many pets do you have. It's like a final set of data. It's not measured. And then now we're down to mean or median, and it depends upon if our data is skewed or not. We see that when looking at our data up above that we have some outliers, such as 0.5 meters, that could skew our data a tish bit. So because our data is slightly skewed, the overlapping would say that the median is the better option to use when looking at the center of our data set. Let's look at measures of spread. Measures of spread, the mean absolute deviation is 0.66 meters. That means, again, that our data is pretty close together. The range is 3.54 and the interquartile range is 0.59. Let's look at the data set as a distribution. I see that the majority of my data lands between 2.5 and I would probably say between 3.99. And if I were to draw the shape of our data, I see that our data is certainly skewed to the left. Which of the following data sets have a normal distribution, meaning there's no skew to them? I would say the first one on the top left is not. Notice that it is very much skewed to the right. I would say that the bottom left is a normal distribution. Similarly, the top right is skewed right since the chunk of our data is on the left and we have some outliers on the right. And I would also say that the bottom right is normal data or evenly distributed. Create a report containing the measures of center and variability along with a dot plot to represent the data. Answer the questions from the CEO using the analyzed data. So here's some information about the number of pencils used per year. The questions that we want to contain an answer in our presentation is about how many pencils do most students use per year? Why shouldn't 60 be included in the new pack, even though 60 is one of the results in the answer? And how many pencils should be included in the new pack? And then if each pencil costs 5 cents, how much will the pencil pack cost? We need some measures of center data and variability to help us answer these questions. Here are the measures of center. The average is 24, the median is 21, the ones that happen the most are 20 and 27, and the measures of variability are for the measure mean of the mean of the average deviation is 6.68, the range is 45, and the interquartile range is 10. This is discrete data since our pencils are counted. We can't count a portion of a pencil. Here we take a look at the dot plot. I see that this is skewed right since the majority of our data is on the left-hand side. Further, we can see from the dot plot and from our measures of center, students use anywhere between 20 and 27 pencils per year. There's only one person who used 60 pencils. The range confirms this, and most people wouldn't buy an extra pencil if they didn't need to have them. Because our data is skewed and discrete, this would lead us to choose the median as the best choice for measures of central tendency, so 21. However, since the mean is only 3 pencils more and would include 6 more people in our data, in this case, the mean would be better serve the general population. If we were to have chosen the median of 21 pencils, it would cost $1.05. If you chose the mean of 24 pencils, your cost would be $1.20. Not much of a difference. Create a histogram to represent the data of the daily high temperatures for June in degrees Fahrenheit. We need to know some information before we can decide how we're going to label our data. So the maximum value is 88 by looking at the table, and the same is 55. Our range is 33. Let's create intervals between 5 or 10. I'm going to go with 5 just because the smaller the better. And I just converted my chart, and I need to identify how many of those temperatures land in each of the ranges that I chose. Since the minimum value is 5, we start with 55 to 59, 60 to 64, all the way up to 89, since our maximum value is 88, but we're still going by 5s. So I see that there are 2 values of our data in the range from 55 to 59, 3 in the range from 60 to 64, and etc. Now we can draw our chart. Notice along the left I have the frequency along the bottom, and I have our temperature intervals that match our table. These little pieces here mean that I skipped some because we don't really care about the data that's happening to the left of here. And now we can start filling in our chart. I see that there were 2 values or 2 frequencies in the range of 55 to 59. 60 to 69 had the same amount. 70 to 74 both had 7, 80 to 84 had 6, and 85 to 89 had 2. Create a box plot to represent the data set. So these are the number of siblings living at home. We need to find the 5 number summary data to create the box plot. This will help us show the 4 equal portions of the data. So we're going to order the data from smallest to largest so that we can identify the minimum, the maximum, the median, and the quartiles. So the minimum and the maximum are 0 and 6. The median is 2. The quartile 1 is 1, and quartile 3 is 3. Well, if you think about it, 3 plus 3 is 3, divided by 3 plus 3 is 6, divided by 2 is 3, so we don't really need to put those extra steps in. We then want to start creating our chart. Putting lines, these are going to be the outlier whisker pieces at the minimum and the maximum points. I then want to place a line at my quartile 1, my quartile 3, so that I can create a box. In the middle of our box will be our median. Further, I want to connect each one of my boxes to the outside. So even though our data is split into even groups, the box plot certainly is not proportional. So it doesn't look proportional, but the data is evenly distributed between here. Because 25% of our data lies within here, 25% of our data lies within here, 25% of our data is here, and 25% of our data is here. Note that 50% of the middle 50% of our data lies within here, so we can identify even the interquartile range from the box plots.